3.6. I'm just going to go through and mark the key points not already on the diagram. So M is greater than 3, inextensible string, smooth light pulley. When it's released from rest, Q moves downwards. P does not reach the pulley, and the tension is 33.6. So let's mark some of those things on the diagram. So the fact that M is greater than 3, this one's heavier, means that when it's released from rest, the system will travel in this direction. And it does say Q moves downwards, so that verifies it. The string is inextensible and the pulley is smooth, so that means that the tension will be the same all the way along the string. The tension pulling against both of the weight forces, 3 times gravity and mass times gravity. So the tension is 33.6. And I haven't used the fact that P does not reach the pulley yet. So first of all, to find the magnitude, to prove that the magnitude of acceleration is 1.4, I'm going to make an equation for P. So for P, in the direction of motion, 33.6 is positive, minus m3g is negative, equals mass times acceleration. So acceleration is equal to 1.4 meters per second squared. For part B, I'm asked to find the value of m, so I'm going to make an equation similar for Q. mg is now in the direction of motion, so mg, and tension is against, so that's negative. So that's the resultant force equals mass times acceleration. So I'm just going to rearrange this to get both of the terms in m on the same side, and g minus, and I'm going to put the acceleration value in there, is equal to 33.6. So dividing both sides by this, I get m is equal to 4 kilograms. For part C, the system is released from rest at time t equals 0. At time t 1 seconds after release, Q strikes the ground and does not rebound. The string goes slack and P continues to move upwards. Find the value of T1. So for C, so we're looking at this motion of Q from here down to here. So I'm going to write down my Suvat conditions. The distance travelled is 10.5. The initial velocity is 0 as it was released from rest. We don't know final velocity. Acceleration we found in part A, and we're trying to find time, which is T1. So if I don't have V, I'm using S equals ut plus half AT squared. So S equals ut, which will be 0, plus half a T1 squared. So rearranging that, T1 is equal to 3.87, so root 15 or 3.87 seconds. Part D, at time t 2 seconds after release, P comes to instantaneous rest. So when Q hits the ground, P will continue to travel upwards. It's worth drawing another diagram for this part of the question. So I'm going to bring this diagram in here. So let's look at this new diagram. So Q is now down here. So at time 0, P was here, it moved up 10.5, and at T1 it's here. we've got to find the time when it comes to instantaneous rest. So imagine this particle hits the floor, the string goes slack, but this is in motion and it will continue to be in motion until it reaches a maximum point, and then gravity will be slowing it down to a velocity of 0, and then it will be speeding up as it goes back down to the ground. There's no tension now acting to pull this, so it's only acting under the force of gravity. So it goes up and then comes back down. So at this point here, we're trying to find the time to get to there. So from here to here to here. Right, so I'm going to write down the Suvac conditions. So I don't know the distance travelled now. Let's just put those in. The acceleration now is minus 9.8 because it's only acceleration due to gravity, and that is in the opposite direction to the direction of motion. That's why it's minus 9.8. Its final velocity we're looking at is 0 because it's instantaneously 0 before it turns and goes the other way. We're trying to find the time for this part of the journey between T1 and T2, and we don't know either of these, but I can find out the initial velocity because when Q hit the ground here, the velocity that it was travelling at would be the same all the way along the string to here. So if I can find the final velocity as Q hit the ground, that will be the same as the velocity when particle P reached this point, and that will be the initial velocity for this next part of the journey. So looking back at here, I can find final velocity. I'm going to use v squared equals u squared plus 2as. So u squared is 0 squared 2as. And so then v will equal 7 root 15 over 5, or 5.42. So I'm going to use the exact value so that I don't have any rounding errors, 7 root 15 over 5. Now I can use v equals u plus at to find the time. So v is 0 equals u plus a, which is minus 9.8 t, and rearranging that for t will equal 0.553 seconds. So the time at t2 will be the time to get to t1 plus the extra time to get to t2. So I need to add those together. t2 will be the time to get to t1, which was 3.87 plus 0.553, and that will equal 4.42 for that part of the journey. The final thing I have to do is to sketch a velocity time graph for the motion of P in the interval 0 to T3. So we've got up to T2. At time T3 seconds after release, the string becomes taut again. So that's when it's travelled all the way up and gets back down to here. It can't travel any further because that would, if the string is taut, that would mean it would have to lift Q off the ground, and Q is heavier than P, so it can't do that. So I'm just looking for this motion to get to T3 over here. So I'm going to draw out a velocity time graph, and I know that part of the velocity is negative. So I need to have a positive and a negative part of the graph. So at time 0, it started from rest. At T1, we know that it was travelling at a velocity of 5.42, and that time to get to there, it took 3.87 seconds. So that was the time at that point. It then travelled under gravity, so it was gradually slowing down. So velocity here was decreasing until velocity got to 0 here, and that was at 4.42 seconds. So it was decreasing under gravity until it got to 4.42 seconds here. It then continued to become more negative. It was speeding up in the negative direction until it gets to here. Now we don't know the time to get to here, but we do know the velocity, because under the weight of under the only force being gravity, this will be symmetrical, and so the velocity here and the velocity here will have the same magnitude, just in a different direction. So if this is 5.42, this will be minus 5.42. So marks wise on this question, there's a method mark for making an equation here, even though you might have some sign errors, and an accuracy mark for the final answer. An accuracy mark for the equation fully correct as well. For part 2, again, there's a method mark for making an equation for Q with some sign errors, and an accuracy mark for the equation correct. Then there's an accuracy mark for 4 kilograms. For part C, there's a method mark for making an equation for the motion of S, and an accuracy mark for all terms correct. So as long as it's clear that you've used a Suvat equation here, you get the method mark with some value, even if you've got some mistakes in your values, as long as it's clear where those values have come from. And then an accuracy mark here for the final answer correct in either form. Part D, a method mark for finding the velocity of the final velocity of the particle. You don't have to have used this equation, but you do have to have found that velocity, and that can be either shown by using the equation or by the answer here. Then there's a dependent method mark for finding the time here, or showing that you're using an equation for finding the time. So that's a dm1, dependent on having done this working out up here. And an accuracy mark for adding together those two values to find 4.42. For the last part, part E, there's a B1 understanding mark for the general shape of the graph correct. Then there's a DB1, dependent, so dependent on that shape correct. There's another understanding mark for all 4 of these values correct.